Hi guys, in this lecture we're going to talk about variance and standard deviation. So before we talk about what those things are, let's recall about what expected value is. So we've talked about expected value of a random variable, x, so ex, and roughly speaking, this is the average behavior in the long run. And that's just the intuitive idea of what is captured by the expected values, the average behavior in the long run. Okay. So the issue with, if I just tell you what the expected value is that you don't really know, on average, how close you're going to be to the expected value or not. So here's the example. So issue is very different distributions can have the same expected value. So, for example, let's look at two distributions with expected value of 0. So, we can have k probability that x equals k. I guess you're going to choose a very simple distribution. Let's say it can be negative 1, 0, or 1, and it has probability 0.25, 0.5, 0.25. Okay. So as I did this, I wanted it to be pretty clear that this has an expected value of 0. So e of x equals 0. Obviously, so if we did this, it would be 0.25 times negative 1 plus 0.5 times 0 plus 0.25 times 1. And the positive and negative cancel out, so you get 0. We could also have k probability that y equals k. This is another random variable. Let's have minus 4, 0, and 4. And again, the same probabilities, 0.25, 0.5, and 0.25. Okay, again, the expected value of y equals 0. But they look very different, right? If we were to plot them, we might have something like that's the probability histogram for x. And for y, right, we'd have, 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Right, it's much more spread out. So by design, the expected value doesn't see this difference. If we spread it out, but do it to the same, increase it the same as we decrease it, on average, nothing changes. So what we want is some way of talking about how spread out a probability distribution is. So what we want, an easy way of talking about how spread out a distribution is. And this is where the variance and standard deviation come. Now, let's see what one might, if you wanted to capture how spread out something is. Let's say that the first idea is, and this won't quite work, so then we'll correct it to what actually works. Let's say, first idea. Let's just take the average difference between the random variable and the expected value. So find average distance between our random variable and its expected value. Right, the idea is that if it's not very spread out, if all the values are very close to the average, then on average the distance will be small. And if it's a very spread out distribution, then on average the distance will be larger. So this distance, this distance is given by x minus e to the x, e of x, the expected value. And I should be using square brackets to be completely precise. So this represents the distance between x and its expected value. So to get average, so this itself is a random variable. Right, this is a random variable. So to get the average value of this difference, we would just take its expected value. So e of x minus e of x. Okay, so this looks kind of trippy, but we can maybe already tell that this isn't going to work. This isn't going to work. And why is that? Well, if we look back up here, let's just look at x, for example. The x is above its expected value, which is 0, just as often as it's below. So x is bigger than its expected value, just as much as smaller. And that's a problem, because the positive and negative distances will cancel out when we take the average. Positive and negative differences will cancel out. And this is a problem because, right, the expected value of x in our example is 0. So from our example, right, the expected value of x equals 0. So the expected value of x minus the expected value of x equals an expected value of x minus 0, which is just x, equals 0. Right, so this is not capturing how spread out this is, because it would give 0 for x and y. And the reason is because we're canceling when it's above the expected value and when it's below the expected value. And in both these examples, it's above by just as much and just as often as it's below, right? Because they're symmetric. So what we really want to do is we want to not just take the difference, but we don't want the positive and negative to cancel out. We want it always to be positive, right? We want to avoid this cancellation. We want something that's always positive. And honestly, the easiest way to do that is just to square things, because then the negative things will be positive and the positive things will be positive. So we square. And this gives us what we call the variance. And this gives us variance. So this is the expected value of the random variable that is x minus its expected value squared. Right. So this might look a bit daunting, but we're actually going to we're going to algebraically manipulate this to be a bit simpler. So if we multiply this out, right, this equals the expected value of x squared minus 2 times the expected value of x. Now remember that the expected value of x is just a number. X is a random variable, expected value of x is a number. Plus, so this is 2 expected value of x times x plus the expected value of x squared. I just multiplied out this parentheses. We can do arithmetic with random variables, it's just fine. And recall that the expected value will distribute over a sum. So this just equals the expected value of x squared minus the expected value of 2 times the expected value of x times x plus the expected value of, well, so this is just a number. Right, so adding it will just shift things, and so it'll shift the expected value. So it's just the expected value of x squared. Alright. Now multiplying by a constant, we'll just multiply the expected value by that constant. So this 2 times expected value here, this is just a number again. So we can pull this outside of our this expected value operation. So what we're left with is expected value of x squared minus 2 times the expected value of x, that was the constant, and then what we're left with inside here is again the expected value of x plus the expected value of x squared. Sorry, of x squared. Alright, so we have 2 times the expected value of x squared plus 1, so this equals the expected value of x squared minus the expected value of x squared. Alright, so this is our formula for variance. Right. So we compute the new distribution of x squared, and then we take the expected value of that new distribution and subtract the square of our previous expected value. Now, the fact that we squared everything will mean that things that are sort of further away will be weighted more, and overall this tells us, this doesn't quite give us the average distance because we've kind of squared everything. So to compensate for that, because we squared everything to make them positive, what we can do is then take the square root afterwards. So, and that gives us the standard deviation. So standard deviation, and this is denoted sigma. And that just equals the square root of the variance. So this equals the square root of the expected value of x, the expected value of x squared minus the expected value of x squared. So this equals sigma. So if it's clear what probability distribution we're talking about, we can just leave it as a sigma, or else we might have sigma sub x to say we're talking about the standard deviation of x. And this is a Greek letter, sigma. This is just the convention. So really all the computation is in computing what's known as the variance, and then what we often, the number we really want though is the square root of that. So we can look at our examples from earlier with x and y, right? So they both had expected values 0. So for x squared, right? K probability that x equals k, right? It had a probability. The square will have a probability distribution of 0 and 1. This was 0.5 and 0. So this is this is the probability that x squared equals k. I'm just squaring the random variable I had up here, right? So 1 and negative 1 will get combined, and so that'll be a probability of 0.5. And so then the expected value of x squared equals 0.5 times 0 plus 0.5 times 1 equals 0.5. While the expected value of y squared, so probability that y squared equals k, and it had values 1 and 4, so it's going to be 0 and 16. So when we square negative 4 and 4, they both go to 16. This is going to be 0.5. It's going to be 0.5. Right, so the expected value of y squared equals 0 times 0.5 plus 16 times 0.5 equals 8. Alright, so then we can compute the variance. So the variance of x equals the expected value of x squared minus the expected value of x equals 0.5 minus 0 equals 0.5. And likewise, the variance of y equals 8. Right, so then standard deviation of x is the square root of 1/2. And the standard deviation of y equals the square root of 8. And this is much bigger than the square root of half. So this number captures how spread out the distribution is. And it gives you an idea of how far away you're likely to land from your average value. Alright, so that's, I guess that's all for the expository lecture. Now we're going to move on to the worksheet. So let x be the result of rolling a fair four-sided die, and compute the expected value and standard deviation of x. So we can't really compute the standard deviation without computing the expected value, but we just want it to be explicit there. Right. So the first step, right, is to make our probability distribution for x, and then the one for x squared. So we have k, probability that x equals k. And we have a four-sided die, so we have 1, 2, 3, 4. And the probabilities are all a quarter, so 0.25, if I can write. 0.25, 0.25, 0.25. And then for x squared, there's no negative value, so there's no outcomes that get combined when we look at x squared. Instead, we just have 1, 4, 9, and 16. And again, the probabilities are all 0.25, 0.25, 0.25, 0.25. So then the expected value of x is simply 1 over 4 plus 2 over 4 plus 3 over 4 plus 4 over 4. And that equals, well, should equal 2.5. 1 plus 1 plus a half, yeah, 2.5. And the expected value of x squared is going to equal 1 over 4 plus 4 over 4 plus 9 over 4 plus 16 over 4. And that equals, there's expected value of x squared. That equals 30 over 4 equals 7.5. So then our standard deviation sigma sub x equals the square root of the expected value of x squared, which is 7.5, minus the expected value of x squared, minus 2.5 squared. And that equals square root of 1.25, I believe. Yeah. And take the square root of this probably. Alright, so it roughly equals 1.118. And our expected value is 2.5. Alright, so for the next question, it's let y be the outcome of rolling a fair six-sided die, compute the standard expected value standard deviation. Basically the same idea. Now you just, it says the six-sided die. I should note, because there's more possibilities and they're all equally likely, we should expect the standard deviation should be slightly higher with the six-sided die than with the four-sided die. But I'll leave that for you guys to compute. Alright, so let's look at this. A gambler is considering playing in two different games which have the same expected value, so we'll have to verify that. Compute the standard deviation of each to determine which is the riskier game. Given are the probability distributions for each game where the random variable represents the profit the gambler makes in dollars. So x1 is the profit, so for game 1, for example, they have 50% chance of losing $4, a 35% chance of breaking even, and then a 15% chance of gaining $10. And then, likewise for game 2, they have these probabilities. So, right, we're going to have to compute the expected values of each to compute their standard deviations. Also, I guess I should say riskier means, I guess, less predictable. So this case, riskier means higher standard deviation. Which is the same as higher variance. If your standard deviation is higher, then your variance is higher, etc., because it's just the square root, or the square. Right, so the expected value of x1 equals minus 4 times 0.5, so that's minus 2, plus 10 times 0.15, which is 1.5. So that equals negative 0.5. That says on average when you play game 1, you'll lose 50 cents. And the expected value of x2 equals minus 4 times 0.25 minus 2 times 0.5. We can ignore 0, right, because 0 times 0.05 is just 0. Then plus 5 times 0.1 plus 10 times 0.1. Alright, so that equals minus 1 minus 1. So there's minus 2 from the negative ones. And this should be 0.1. My bad. We have plus 1 plus 1.5. So minus 2 plus 1.5 equals minus 0.5. So again, on average, playing game 2, you'll also lose 50 cents every time. Or not lose 50 cents every time, but rather you'll lose 50 cents per game on average. Alright, so now what we need is the expected values of the squares of these variables, and we can compute the standard deviations. And we should expect that game 2 will have a lower standard deviation because we don't have, not all of the values are pushed out to the extremes. Potentially, but there's also a higher value of 0 in game 1, which is pretty close to the expected value too. So it's actually hard to say intuitively which one is going to have the higher standard deviation, but then that's why this is an exercise. Right, so let's compute the standard deviation for game 2, and then I'll leave you guys to compute the standard deviation of game 1, which is a little easier anyway, and to compare them. So the first step, right, is to compute the probability distribution for x2 squared. Alright, so we have negatives, which will be made positive, but we don't have any values that end up overlapping, just coincidentally. So the smallest value is 0, and that'll be 0.05 again. And then will be 4 from squaring 2. So 4, and that will have a probability 0.5. And then the next will be 16 with probability 0.25. And then probability, and then 25 with probability 0.1, and then 100 with probability 0.1. Alright, so now you need to average, or not average, but find the expected value of this. So then expected value of x2 squared equals 4 times 0.5 plus 16 times 0.25 plus 25 times 0.1 plus 100 times 0.1. Alright, oops. And you add this together, and you'll get 18.5. Alright, so then the variance of x2 equals 18.5 minus the expected value of the variable, which was minus 0.5 squared. That's important, right, because now this negative value is becoming positive. And this equals, so 18.5 minus a quarter is just 18.25. So that's the variance. And so then the standard deviation of x2 is equal to the square root of 18.25. Okay, so that tells you how spread out it is on average. And then what you need to do is do the same thing for x1. So do the same for this one, and compare. That's all for this lecture. I'll see you in the next video.